Hello everyone, welcome back to the second part of our least square lecture. And in this lecture, we are going to see a different kind of problem, which is not very different, pretty similar, but still a little different. Anyway, let's just move on. So the problem is finding the best fit line. So you have some data, you're trying to find the best line that fits with the data. So this is called linear regression. So let's just say we have the price of milk here, and one day you noticed that if the price of milk increases, the price of milkshake also increases, which shouldn't have been a surprise because, well, milkshakes are made with milk. So yeah, so as you can see, if the price of milk when it was 30, the price of milkshake in your local store was 42. When the price of milk was 40, the price of milkshake became 53. When it was 50, this became 58, and so on, blah, blah, blah. All right. So as you can see, there is a clear relation. We call it correlation of these two variables. The price of milk increases, the price of milkshake also increases. So this is a correlation. And if you plot the data, this is my data. There is one mistake. The data shows 53. In my graph, I have written 52. So this should be 53. But other than that, okay, so this is your data. This axis is the price of milk. Y-axis is the price of milkshake. And as you can see, it kind of looks like a line. Not exactly a line, but kind of looks like a line. So if you could find a line that would exactly match this, something like this, that would be really good, because then you could estimate the price of milkshake based on the price of milk at any point. For example, if the price of milk was 60, the price of milkshake would be something like 70, right? So the price of milkshake would be something like 70. If the price of milk is 90, 80, please note that you don't actually have any data for it, but using this approximation or estimation, you can foretell whatever the word is, I don't know. The price of milkshake is going to be something like 84 or something. Sorry, 90. Let's just call it 90. So something, I think this is going to be 90. Yeah. So this is the line that fits the data best. So my errors, this is my error, this portion. So the difference between the actual data point and my line is the error. So I want to minimize this error. So these distances, I want to minimize the square root of this distance. Distance 1, let's call it distance 1, distance 2, distance 3. So this, I want to minimize these distances of my line. So the line with the minimum distance is my best estimation. So as you can see, this is a least squared. Actually, this is why we call it a least squared problem, because we want to minimize this term. Anyway, so this is where the name came from. And if you remember our last video, we were trying to, this was our actual vector, and this was our projected vector b hat. This was my error. The distance between the actual vector and the projected vector was my error, right? And we were trying to minimize the error. And the minimization would occur for the projected vector. And you know, the distance between two vectors is also the root over x1 minus x2 square plus y1 minus y2 square. So that's where the least square term comes from. We want to minimize the squared summation, root over of the squared summation. Anyway, I got sidetracked. So as you can see, the problem here right now is to find this line. Now, I don't know how to find this line. I don't know anything about this line. I even drew this line based on just the point. So eyeballing it, to be honest. I don't know the slope of it. I don't know the exact line that would minimize it. And to find that is to solve the best fit problem. So let's see. So this is the equation of a line. I need to find the values of m and c. If I know what m is and c is, I'm going to find my line, right? So these are the two variables, m and c, that I need to know. So this is my data. I can just write it as an equation, which is 42 is equal to 30. Oh man, I made a mistake. This should be m. All of this should be m. because my variable is m, not x. Okay, so I know 30 into m plus c. For sum n and c, I get this. This comes from my data, which is this one, right? So, okay. But as you can see, we don't actually have a line that goes through each of these points. So there is no exact solution here. If I convert this into a matrix, this linear system of equation will not have an exact solution for m and c. There does not exist a single line that goes through all of the points. So what we have to do, and you guessed it, we have to find the best approximation, and we just did the same thing in our last video. We have a, x, and b, which is probably going to come up here. I shouldn't have written that. Anyway, so you know how to solve it. We are going to multiply both sides with A transpose. Then if I do the multiplication, this is going to be the result. Don't worry, you are not going to get such huge numbers in the exam. I just created a random example, so the numbers are a little ugly. And in real life, when you are dealing with hundreds and thousands of data, you are not going to do the multiplications yourself. A computer and the software will do that for you, so don't worry about that. Anyway, you just need to know that what we are doing. We could not solve ax equal to b, so we are going to multiply at on both sides, and we are going to find the solution of that system, which is going to be my best solution of the original system. All right, so this is my original system. I'm going to find the best approximation for this. Okay, so where were we? Yes, we did the multiplication. If I perform a row operation process, if I convert this into a reduced to echelon form, my system looks like this. So as you can see, m is equal to 0.93, c is equal to 13.98. So if you put that values here, you get the equation of a line, right? So y is equal to 0.93 into x plus 13.98. This is a very nice equation of the line. Let's put that line in our graph, and as you can see, this is my best fit line. Looks good, right? Okay, so that is how you do a best fit approximation. And again, I just want you to remember that when you are doing this, when you are in this phase, don't do row operations. This is an inconsistent system. If you do row operations, you are going to create a new data, something like you are going to create, let's say you add these two, you are going to create 72 is equal to 4253, which is 95, which means when the price of milk was 70 and the price of milkshake, oh, you have to divide it by 2 again, so 35, 1 and 47.5, I think. So you created a new data, right? When the price of milk was 35, the price of milkshake was 47.5, which is not a data. You just created a new data, which is going to affect your answer. So don't do row operations before you multiply with a transpose. I just wanted to remind that to you again. All right, so that's done, and that's done. So that's done, and we got our best line approximation, and that's it, voila. So yeah, that's your lecture 16 done. I hope you liked it. This is quite nice, and in many cases, in many linear algebra courses, people would teach you how to do the just the math that you get a system, it is not solvable, just multiply a transpose on both sides and you'll get something. But a lot of students don't get to know why they are doing it and why they are multiplying a transpose and what does it actually mean geometrically. So I hope you got a very clear picture of that, and that would be all for today. Thank you for watching, and I will see you in week 10, I guess. Up until then, thank you. The next topic we're going to be learn is eigenvalues and eigenvectors in week 9, which is going to be taken by Sabah Fatima Miss. So I hope you enjoy that too. Good night.